All right, so this is the design for manufacturing review for Mech 2. Some of this stuff is probably going to seem pretty familiar, pretty similar to the things that we learned in DML. And of course, you can find all of the design for manufacturing tips on the website for DML. But today we're just going to go over a couple of the key points that we're going to hope to use and apply in this class moving forward with our designs. So the goal of design for manufacturing, of course, is to save money. And we do that because if our part takes less time to make, then that means that it costs less. And of course, we're going to want to make sure that it's as easy as possible for the manufacturer, because if he understands it and he gets it and he can do it as quick as possible, then that saves us some money. So we're going to go over some general things first, and then we'll get into some more specific things that we want to hit on. First thing we're going to go over is minimizing the number of datums that we use. So it is okay to have more than one datum, but we're going to want to make sure that there's a pretty good reason for that. And here's the reason why. If I'm the manufacturer and I'm looking at your drawing and there's one datum, then I can find every feature from that same point. So I zero off on one side and I can find all the features, boom, I'm done quickly. But if there's a datum here and there's a datum halfway through and there's a datum 3/4 of the way through, now I'm having to measure all of these different places. It's taking me forever to find your features, and that costs money. And so we want to minimize the number of datums that we use and make sure that we have optimized that to the best of our ability. We also want to make sure that we minimize the overall part size. Of course, some parts just can't be any smaller, but as a general rule, we just want to make sure that they're as small as they can be, because smaller parts require less raw material, which of course saves us money. We also want to try to use symmetry whenever we can. So you can see we want to make sure that instead of using a left and a right version as two unique parts, we want to try and make one part that can be used for the left and the right. Because if we have one part instead of two, then of course that saves us money as well. A left and a right require different setups, different fixtures, and the manufacturer is going to have to make one part and then a part that looks just like it, but it's different. And that could cause problems. So we want to make one part that works and they can just duplicate that part as many times as needed. We also want to make sure that we take advantage of off-the-shelf parts without taking too many off-the-shelf parts. So simple things like spacers and bushings, we want to make sure that we take those from people that have already made them. But if we buy too many off-the-shelf parts for our design, we might actually be making it more difficult for us to try and fit all of these off-the-shelf parts together rather than designing our own parts and taking advantage of spacers or bushings, things that people have already made. Now we're going to get a little more specific. We're going to talk about tolerances for a little bit. We first of all want to make sure that we use as large tolerances as we can wherever it's possible. Because a large tolerance means that it takes less time to get within the range, but a small tolerance means that it takes a while because the manufacturer is going to have to figure out the range. He's going to have to spend a lot of time cutting off a little bit till it gets within the range, and then he can stop. But if the tolerance is pretty large, he can take off a chunk, boom, I'm in the range and I can move on to the next feature. We also want to consider the importance of every dimension when we're tolerancing. And so as we can see here in the figure below, our feature 1 is 2 millimeters and the tolerance is plus or minus 0.1 millimeters. Now that seems reasonable. When you look at number 2, it's 200 millimeters, but the tolerance is still plus or minus 0.1 millimeters. Now, for number 1, that tolerance seems pretty reasonable. It's 2 millimeters and there's the tolerance. But that second dimension is 200 millimeters, and that might just be the distance or a gap or something. But that 200 can possibly be as important as that 2 millimeters. And so those tolerances, of course, shouldn't be the same. We can see that maybe 205 millimeters wouldn't be all that different from 200. And so clearly that tolerance needs to be relooked at. We also want to use standard tolerances rather than changing the tolerance for each feature. So if there was a tolerance, or if there were more features on this drawing below, and if one was duplicated a couple other times, we would want to make sure that those tolerances stayed the same instead of changing it for each one. If those tolerances are the same for each feature, then the manufacturer can look at it, he'll see, okay, well, the tolerance is the same. I know the tolerance. I'll make this first one good. I'll make this second one good. But if they're different, he'll make the first one, then he'll have to refer back to the drawing again. What's the tolerance? Figure it out. And then he'll have to go, it'll take a longer time if the standard tolerances aren't used for each feature. And so this is where our tolerance loops can come into play, because if you do your tolerance loop and you find that your tolerance is larger than the standard tolerance, then we can just go ahead and use the standard tolerance because the manufacturer knows it, it's there on the drawing, and it's not going to take them any longer to make it. Now we're going to take a little bit of time to talk about some of the holes that we use in our drawings. Of course, we have done this before, but if you're on the mill and you've got this thick piece of metal, aluminum, steel, whatever it is, and you take that mill and you bring it down and you go straight through, that is so much easier than having to zero off on the top and then looking at the drawing and then finding out, okay, well, I have to go half an inch down or however, whatever the dimension is. Then you have to look at the DRO and then go down and make sure you're within the tolerance. I could have gone straight through and been done in 10 seconds. So we can see how through holes are much easier to manufacture than a blind hole. But sometimes blind holes aren't avoidable. We have to use them. We want to make sure that we use a cone bottom rather than a flat bottom unless it's absolutely necessary. If you might also recall, the flat bottom requires an extra step because that's a separate tool that makes that bottom flat instead of a cone bottom. And of course, we want to remember the tool stiffness and the strength. And so the length to diameter ratio for those drill bits needs to be at 8:1 or less. The less, the better. Because if it gets too long and too thin, it'll start to get wobbly. That strength is decreasing rapidly. And if our ratio is higher than that 8:1, then we're not sure what could happen. The heat could cause problems. We know that the strength is weakening and it could ultimately lead to failure because we haven't been keeping track of that ratio. So here's a quick example. If our hole is 1/4 inch, we want to make sure that it doesn't have to be drilled more than 2 inches deep, because as we can see, that ratio would have to be, it'd be 2 inches in length, 1/4 inch in diameter. That would be 8:1. Now we're going to talk about the tools for a second. We want to make sure that we use standard sizes. With the metrics, it's like an M6 or an M8 or an M10, something like that with the integers for the mils. And if it's in inches, then it's going to be like a 3/16 or 7/16 or 9/16. Of course, those other fractions are going to simplify. So we want to make sure we use standard sizes because those are going to be easy and simple for the manufacturer to use. And also if we're using a CNC, we're going to want to make sure we use simple standard sizes as well so that it doesn't take extra time getting to those different dimensions. Lastly, we're going to take a look at our material selection because yes, of course it does matter. Now in DML, you might recall that we used aluminum unless we had to weld something. And so in this case, we know that steel is 3 times harder to machine than aluminum. And that's basically why we used aluminum. And so aluminum is easier to machine than steel, but it's harder to weld on aluminum than it is steel. So if you don't have to weld, then it's better to use aluminum. But if you do, then steel is our better option. Moving on, stainless steel, titanium are even harder to manufacture, or the manufacturability is even harder than steel. And so we want to make sure that we take into account the manufacturability of the materials that we use when we're comparing the other things such as strength or elastic modulus and the other properties that the material has. And also we want to keep in mind that some polymers like PVC or things like that, those are even easier to machine, but we can run into some other problems because we know that they're not as strong as some of the metals. They could also run into thermal problems with the heat of those machines, and plastic can heat up very quickly. We know that we could run into some other issues with maybe warping or things like that. And we want to use the raw material shapes that are available to us to minimize the material removal as well. Because as I mentioned before with the warping, if we remove a whole lot of material from a piece, for instance, if we use that square and make it into an L bracket, it's going to be warped when we finish because we've removed so much material that it's been hot for so long. It's changing the properties and the shape of that material. So we're going to want to make sure that we use raw material shapes to minimize the material removal whenever possible. That's all I've got for you guys, and I hope you take this into account, use these design for manufacturing tips, and make it easy to manufacture your parts coming up this semester. All righty, see you guys.